Now I know that these group of complex numbers exist. I can go to my log tables on page 23 and look at all the different groups of numbers. So we've natural numbers and they give us examples. Integers, the notation is Z for integers, plus or minus whole numbers including 0. A rational number is any number that can be written as a fraction, where the top number has to be an integer and the bottom number has to be an integer. And a real number is any number on the real number line, like we were talking about in the last video. And complex numbers are anything that can be written in the form of a plus bi, where a and b are any real number. So even the number 7 can be written in complex form, so 7 plus 0i, and so on. Now, since these numbers exist, I need to be able to do what I normally do with any numbers. So add, subtract, multiply, divide. So if I pick 3 plus 2i, that's one number. And I want to add another complex number to it, 4 minus 4i. I have the 3 and the 4, which is 7 plus, minus 2i. So as I would with any unknown number, I can treat this, similar to algebra. I add the like terms and I end up with 7 minus 2i. If I want to subtract those terms, 3 plus 2i minus the 4 minus 4i, that's 3 plus 2i minus the 4 plus the 4i, which gives me minus 1 plus 6i. If I want to multiply the two terms, 3 plus 2i by 4 minus 4i, I would do this exactly like I would do in algebra as well. I have 3 by the 4, which is 12, plus the 2i by the 4 is an 8i, minus the 3 by the minus 4i is the minus 12i, and the minus by the plus is a minus. 2 by 4 is 8, I by I is I squared. So that gives me 12 plus, 12 minus 4i minus 8i squared. Now if I take a look at I squared, well, I is the square root of minus 1. Therefore, if I square it, I get the square root of minus 1 to be squared, which is just minus 1. So anywhere I see an I squared, I can replace it with minus 1. And I end up with 12 minus 4i plus 8, which is 20 minus 4i. If I want to divide in complex numbers, again, I'm treating it like algebra. If I want to simplify anything or divide anything, I can factorize the top line. That gives me 5 times 3 plus 2i all over 5. And I can simplify that. If I come to trickier or questions that aren't that straightforward to do with division in complex numbers, such as 2 plus 11i all over 2 plus I can't divide in here. I can't factorize the top line or factorize the bottom line. So I'm going to have to use a little trick. I'm going to multiply above and below by the number 1. But I need to carefully multiply. So I could multiply by 5 over 5 or 10 over 10. That would be multiplying by the number 1. But I'm going to multiply by 2 minus I. I'm going to multiply the conjugate of the bottom number. And this will get it to get rid of the complex number on the bottom line. So I'm going to have, I'm going to have a real number on the bottom line. Multiplying this out top by top. 4 minus 2i plus 22i minus 11i squared on the top. And 4 plus 2i minus 2i minus I squared on the bottom. They cancel off, which is what I want in this situation, because I'll end up with just real numbers in the bottom line. So that is 4 plus 20i minus 11 times I squared. I squared is minus 1 all over 4 minus, and again I squared is minus 1. In the top line I end up minus by minus is plus. So that's 4 plus 11, which is 15, plus 20i all over 5. And I'm going to simplify this as I would any fraction. 5 is in common. I'm left with 3 plus 4i all over 5. And simplify it down, my solution is 3 plus 4i. So in case we can't do, you know, the skills we've learned before, maybe perhaps long division in algebra, or just it's not a straightforward question, I have to be able to do this type of skill where I multiply above and below by the conjugate of the bottom number. In case you see the notation, if they said z is 3 plus 2i, and they asked for that, that's the conjugate of z, that's just 3 minus 2i.